Welcome to Maths with EJD. We're still talking about applications of eigenvalues and eigenvectors. Here, the focus is on vibration analysis in mechanical engineering, or maybe even other aspects of engineering like civil engineering and the rest of them. So, because we're talking about vibrations. So, the overview in mechanical systems, eigenvalues and eigenvectors play a fundamental role in determining the natural frequencies, natural frequencies and mode shapes of vibration. Understanding these properties. So here, I mean, natural frequencies, you know, natural frequencies, they are key concepts as well as mode shapes. Okay. So understanding this, okay. So understanding these properties is crucial for predicting how a system will respond to dynamic loads, ensuring that mechanical structures and machinery operate safely and efficiently. Okay, of course, the objective of this is to learn how to apply eigenvalue analysis to determine the natural frequencies and mode shapes of a mechanical system. So let's look at an example like that of a spring mass system. So consider a simple spring mass system governed by the equation mx dot dot plus kx equals 0. Of course, mx dot dot means the squared x, the t squared. That's it's talking about time. So where m is the mass matrix, the mass matrix, the mass matrix. K is the stiffness matrix, We're talking about some kind of elasticity here. Then X is the displacement vector, the displacement vector. Now, to determine the system's vibration characteristics, the system's vibration characteristics, characteristics, we solve the eigenvalue problem. We solve the eigenvalue problem. K minus lambda m, v equals 0. Again, where lambda represents the eigenvalues which correspond to the squared. So the eigenvalue you get is equal to the squared natural frequencies. Natural frequencies. Okay. So in short, we're saying that eigenvalue lambda is equal to the square root, the squared natural frequency rather. So that eigenvalue is natural frequency raised to power 2, which implies that natural frequency is square root of eigenvalue. That's the essence of that. Then what else do we have? We have V, right? Which will represent the eigenvectors. So V represents the eigenvectors. The eigenvectors which describe the mode shapes, of vibration. Okay. So let's go for the data. Let's assume the following. Let's assume the following mass and stiffness matrices. Okay, that the mass matrix is 2, 0, 0, 2, while the stiffness matrix is 6, -2, -2, 6. Okay, so the next thing we want to do is to solve the characteristic equation. Solving the characteristic equation, the characteristic equation. So we have the determinant of k minus lambda m as stated up there equals 0. That means determinant of what is k now? K is 6 -2 -2 6, then minus lambda m. So that is 2 lambda, lambda m. So that's lambda times 2, 0, 0, 2. So that's lambda m 0, then 0, 2 lambda. Okay. And that is equal to 0. So that means we have 6 -2 lambda, then -2 here, then -2 again, then 6 -2 lambda, and that is equal to 0. So as usual, we have multiply this. That's 6 -2 lambda squared minus 2 squared again, and that is equal to 0. So if you square this, I mean, fast math mental tricks. So 6 squared minus 2 into 6 into 2 lambda plus 2 lambda all squared. That's how that goes. Minus 4 equals 0. So we have 36 minus 2 times 6, 12. That's 24 lambda, right? Plus 4 lambda squared minus 4 equals 0. So if you tidy up all of that, we have 4 lambda squared minus 24 lambda. 36 minus 4 is minus 32. I mean, it's plus 32. Yeah, plus 32, and that is equal to 0. We can divide through by 4, right? We can divide through by 4. So we have lambda squared minus 6 lambda plus 8 equals 0. So what do? We need to factorize. 2 times 4 is 8, and 2 minus 4 is minus 6. So we can quickly go lambda squared minus 2 lambda minus 4 lambda plus 8 equals 0. So that means we have lambda into lambda minus 2 minus 4 into lambda minus 2 equals 0. So that means we have lambda minus 2 into lambda minus 4 is equal to 0. So that's coming well. So we have just our two lambda. So we have lambda minus 2 equals 0 or lambda minus 4 equals 0. So that means that we have lambda to be, so we can say lambda 1 is 2 while lambda 2 is equal to 4 or any other. I don't think it matters. So from there, we can go ahead and compute the natural frequencies. So talking about the natural frequencies now. So natural frequencies, and we got the formula the other time. The natural frequencies would be the square root of eigenvalues. So we say the natural frequencies omega are given by first we have omega 1, which is square root of lambda 1, that is square root of 2, and that is approximately 1.41. Then we have omega 2, which is square root of lambda 2, that is square root of 4, which is exactly 2. So like that. Of course, I'm still going to show the Python code, but let me go for the key takeaways before I do that. So the key takeaways in this case, the key takeaways, of course, we can get the corresponding eigenvalues, right? Eigenvectors. I guess we should do that, all right? Okay, I think let's do the eigenvectors. Let's get the eigenvectors. Okay, so eigenvectors now, eigenvectors. So, I mean, since we have 2 and 4 as the eigenvalue, so we can just go back here. We can go back to this place. So we have 6 minus 2 lambda minus 2. So with, so, um, um, so that'll be the determinant, right? We have so that will now be, let's look at what we have again. Yeah, for eigenvalues, it's still the same standard procedure. Okay, now we have k minus lambda m, okay? So k minus lambda m. So for eigenvectors, for the eigenvectors, we have k minus lambda m multiplied by the vectors equals 0, basically. So that means that um we have the absolute value, not no absolute value this time around. We just have 6 minus 2 lambda minus 2, then minus 2, 6 minus 2 lambda. All right, that this is k minus lambda m into v, let's say v1, v2, and that is equal to 0. So now we have two different kinds of lambda. It can be 4, it can be 2. Lambda 1 is 2, lambda 2 is 4. So let's go for lambda 1. So for lambda 1, which is equal to 2. So we can have this expression rewritten this way because lambda 1 is 2. So we have 6 minus 2 times 2. This is minus 2, minus 2, 6 minus 2 times 2 again into v1, v2, and that is equal to 0, 0, like that. So 6 minus 4, right? That's 6. Let's go straight from here. 6 minus 4 is 2 minus 2 and minus 2, 2. Okay, and that is v1, v2 equals 0, 0. So we have, of course, just like what we always do. So we have, so we have 2 multiplied by v1 and minus 2 multiplied by v2. That is 2v1 minus 2v2 equals 0. That implies that 2v1 is equal to 2v2 and v1 equals v2. So if you do it for the other one too, it's exactly the same thing, okay? So if you do it for the other one, it's exactly the same because now you have this and that. So so this will be minus 2 times V1, then 2 times V2. That's minus 2 V1 plus 2 V2 equals 0. Again, that's still 2 V2 equals 2 V1. So again, V1 is equal to V2. So in short, we can just take any random value. So we can say if, so we can say that if V1 is equal to 1, then V2 is also equal to 1. So we have the eigenpair, eigenvalue 2, then eigenvector 1, 1 transpose. So that's the eigenpair for that. So we use the other value, which is 4. So for lambda 2, which is equal to 4 now, we go back to that expression again. That's 6 minus 2 times 4. 2 lambda minus 2 minus 2, 6 minus 2 times 4. Okay. And that is again V1, V2, and that is equal to 0, 0. So we have 6 minus 8, that's minus 2, minus 2, minus 2, minus 2, V1, V2 equals 0, 0. So the expressions, so this and this will go. So we have minus 2V1 minus 2V2 equals 0. So this simply tells us that minus 2V1 is equal to 2V2. So in short, we have V1 to be equal to minus V2. So if you do it for the second one, it's the same thing, okay? So if V2 now, or rather, if V1 is equal to, we can also rewrite this as V2 equals minus V1, okay? Maybe this is a better way to write it, but it doesn't matter. Anyone can come first. But yeah, I think it's okay. Yeah, it's okay. So if V1 is 1, then V2 is minus 1. So we have the eigenpair. We have the eigenpair 4, comma 1 minus 1 transpose. So so we have got we can now conclude that therefore the eigenvalues are 2, 4 corresponding to the eigenvectors 1, 1 and 1 minus 1 respectively. Okay, so we can then talk about the takeaways in this situation. So let's talk about the takeaways. Before we talk about the Python code and then round off. So first of all, eigenvalues correspond to the squared natural frequencies. So from the eigenvalues, we can get the natural frequencies. Basically, that's all that is talking about. Then next, eigenvectors. The eigenvectors actually can be also seen as the mode shapes. Describe how the system vibrates at each frequency. Okay. And lastly, we can say this, that engineers must design systems to avoid resonance, which can lead to excessive vibrations and structural failure. So this kind of analysis can really help us to see to prevent this structural failures. So doing this kind of analysis, which eigenvalues can help with, actually can go a long way. So let's look at the Python code corresponding to this. Yep, so we have it, vibration analysis. So this is it right here. Now, we define the mass matrix, we define the stiffness matrix as given. Then we get the eigenvectors and eigenvalues and eigenvectors in line 12. Then the natural frequencies, we know that's the square root of the eigenvalues as defined in line 15. Then we want to, so this show us the results. Then all this can now show us the masses, like uh, this can we can now visualize all this. So if I run this now, we have the results coming. Okay, so just like we got eigenvalues 4 and 2, the natural frequencies corresponding to them 2 and 1.2, 2 and root 2 if you like. Then the mode shapes. Now, because I mean this one has been because of the summary, because of the abbreviation here, if I use 1.414, I'm going to get it, but this is more or less like 1 1 minus 1 1 that I did the other time. So this is fine. So, and these are the masses that will corresponding to that. Okay. So this is for mode shape 1, where omega is the natural frequency is 2 radian per second. Then mode shape 2, where the natural frequency is 1.41 radian per second. So this 0.071 you're saying is when you use the numeric, the square root of 2 to be 1.41 and all that. So, but I mean, from what we have, this is how it goes. So, if you have not if you have subscribed to this channel, thank you so much for doing that. But if you have not subscribed, please go ahead and do that, because there's a lot more to still learn. Because I'm still going to talk about applications of eigenvalues and eigenvectors in Google page ranking, for instance, page rank algorithm for Google. Then I'll be talking about how it applies to population growth or population modeling. Then I'll talk about how it applies to image compression. So there's still a whole lot to learn. So hit the notification bell, and so you can always get alerted anytime a new video is released. Then comment, let me know how helpful these videos are, and let me know if there's a topic you like me to, a problem you like me to solve. Also, like and share so that more people can have access to this great content. Till I come your way again, keep doing much right. Bye.